10 of the last 10 years were the hottest in recorded history. Not 9, not 8, all 10 in a row without a single exception. And 2024 didn't just beat the previous record, it obliterated it. The year was the warmest since global records began in 1850, and it came in more than 1.5 degrees above the pre-industrial baseline. The threshold the Paris Agreement was built around, crossed in a single calendar year. And the part that doesn't make headlines, it's not just hot, it's speeding up. Earth has been warming at an average of about 1/10 of a degree per decade since 1850. Since 1982, that rate has more than tripled. 3 times faster. Not gradually, not linearly. The most recent decade was hotter than any previous decade on record, and a study published in 2026 found concrete statistical evidence that warming has genuinely accelerated, not just continued. We are not watching a slow fade. We are watching a system come undone at the seams, faster than the models predicted, faster than the headlines suggest, and faster than most people realize. If that's the kind of thing you want to understand, not just the headlines, but the actual physics, the actual history, the mechanisms, the turning points, subscribe and hit the bell. Every video on this channel goes past the surface, and this one goes very deep. Because before we talk about what's coming, we need to talk about how we got here. And that story starts not with a policy summit, or a protest, or a disaster. It starts with one man on top of a volcano, staring at numbers that didn't make sense to anyone but him. March 29th, 1958. Mauna Loa Observatory, Hawaii. The summit of the largest active volcano on Earth, almost 4,000 meters above sea level, wrapped in clouds and stripped of anything that might contaminate the air. Charles David Keeling had started his scientific career as a chemist at Caltech, studying groundwater in the wilderness of Big Sur. That was his world. Quiet, methodical, precise. He wasn't a climate crusader. He wasn't looking for a signal from the future. He was a geochemist who cared obsessively about accurate measurement. And in the mid-50s, a specific question started pulling at him. Was the carbon dioxide in the atmosphere actually constant? Scientists had assumed it was, but nobody had really checked. Not rigorously, not continuously, not with the right equipment. Around 1956, Roger Revelle, the director of Scripps Institution of Oceanography, invited Keeling to perform atmospheric CO2 measurements for the International Geophysical Year. Keeling had proposed that he could deploy a new analytical tool, an infrared gas analyzer, to take continuous readings directly from the air. The instrument was new, expensive, and considered by many of his seniors to be overkill. They were skeptical. They argued that CO2 in the atmosphere was too variable to justify high-precision measurements, and that the volcano itself would contaminate everything anyway, belching its own CO2 and ruining the data. Keeling ignored them. Mauna Loa was specifically chosen because of its remote location, far from continents and vegetation. Keeling and his team measured the incoming ocean breeze above the thermal inversion layer to minimize any local volcanic contamination. The data was then normalized to remove any remaining influence. This was science done with watchmakers' patience. On March 29, 1958, the first reading came in. 313 parts per million of CO2 in the atmosphere. 313. At the time, that number meant almost nothing to anyone outside a small circle of atmospheric chemists. The pre-industrial baseline, known from ice cores, was around 280 parts per million. Keeling's first measurement was just slightly above that pre-industrial level. The gap looked small, barely noticeable. But Keeling kept measuring, day after day, month after month. And something extraordinary happened. He noticed the atmosphere was breathing. In the northern hemisphere, CO2 rose in winter when photosynthesis slowed, then peaked at the start of spring. When leaves emerged and photosynthesis accelerated, CO2 was drawn back down. The curve showed this annual inhalation and exhalation, a seasonal rhythm of the planet's atmosphere that had been completely invisible until that moment. The graph zigzagged like a heartbeat. The Earth was breathing. And every year, the baseline of that heartbeat was slightly higher than the year before. By 1960, Keeling had two significant findings. The first quantitative estimate of Earth's natural seasonal CO2 oscillations, and, more alarming, a steady annual increase in atmospheric CO2, year over year, without exception. The numbers were going up. Steadily, consistently, in lockstep with the industrialized world burning coal and oil beneath his measurements. Keeling spent his entire career measuring atmospheric CO2, and plenty of time and energy fighting to keep the project alive. Some colleagues questioned why sustained monitoring was even necessary. Budget cuts eventually forced him to abandon his South Pole station in the 1960s. But the Mauna Loa measurements never stopped. A gap in 1964, when underfunding briefly halted measurements, remains the only interruption in the entire record. At one point, Keeling was ordered by funding administrators to guarantee 2 discoveries per year. 2 discoveries per year. The man who was producing what would become the most important environmental dataset in the history of science was being asked to justify his budget like a salesman hitting quarterly targets. He posted the running data, the climbing curve of CO2 concentrations, on the wall directly across from his office. He looked at it every day. Every year, the numbers went up. 320, 330, 340. Year after year, the slope didn't flatten. It climbed. According to Naomi Oreskes, professor of the history of science at Harvard, the Keeling curve is one of the most important scientific works of the 20th century. It is the longest continuous record of atmospheric CO2 ever assembled. And what it shows across more than 65 years is a single, relentless upward curve, with the seasonal breathing of the biosphere riding along its surface like waves on a rising tide. From 316 parts per million in 1959, the curve climbed all the way to 425 by 2024. Keeling died in 2005. His son Ralph took over the measurements and carries them on to this day. The program has been interrupted only twice, once by a funding crisis, and once in November 2022, when lava from the volcano blocked access to the observatory itself. Even Mauna Loa tried to stop it. It didn't work. I'll be honest about something. The story of Keeling is deeply uncomfortable in a way that goes beyond the climate data. Here was a scientist doing something that every scientist is told to do. Measure carefully. Report honestly. Let the data speak. And what he got for it was decades of budget fights, institutional indifference, and the crushing sense that the people who should have been most alarmed by his numbers simply did not want to look at them. The curve he drew still matters more than almost anything else in climate science. Because every question about whether warming is real, whether it's accelerating, whether it tracks with industrial activity, runs directly through that jagged, climbing, merciless line on the wall of his office. So what exactly is that line telling us? What does carbon dioxide actually do to a planet? The word greenhouse is one of the most misleading terms in all of science communication. A greenhouse works by blocking convection, by stopping warm air from rising and escaping. Earth's atmosphere doesn't do that. What it does is stranger, more elegant, and ultimately more alarming. Here's the actual physics. Sunlight, visible light, passes through the atmosphere almost freely. It hits the surface, warms the ground and the ocean, and then the surface re-radiates that energy back upward. But it doesn't re-radiate it as visible light. It re-radiates it as infrared radiation, a longer wavelength, which we experience as heat. Not all gas molecules can absorb infrared radiation. Nitrogen and oxygen, which make up more than 90% of Earth's atmosphere, are completely transparent to it. But CO2 molecules can vibrate in ways that simpler molecules cannot, which allows them to capture those infrared photons. Picture it this way. The atmosphere is like a room full of billiard balls, mostly transparent, mostly inert. Nitrogen and oxygen are like glass balls. The infrared passes right through them. But CO2 molecules are more like rubber balls. They grab the infrared photon, wobble with the energy, and then release it in a random direction. About half of that re-emitted energy goes back out to space. The other half comes back down toward Earth, contributing to warming at the surface. This effect is so powerful that we get almost twice as much heat from our own atmosphere as we get directly from the sun. That is the greenhouse effect. Infrared radiation bouncing between Earth's surface and the lower atmosphere 24 hours a day. It's why our planet averages 60 degrees Fahrenheit instead of frozen space. It's why life exists here at all. So the greenhouse effect is not the problem. It is the foundation of life on Earth. The problem is the dosage. Before the Industrial Revolution, atmospheric CO2 sat at around 280 parts per million. During the Ice Age cycles of the past million years, it never got above 300. That ceiling held for 800,000 years. 800,000 years of glacial cycles, of sea levels rising and falling, of ice sheets building and retreating, and CO2 stayed in that band. It was a climate regulator, not a runaway driver. Then we started burning things, and the ceiling broke. Atmospheric CO2 hit 422 parts per million in 2024. That is 50% above the pre-industrial level, and higher than at any point in the last 3 million years. When CO2 was last this high on Earth, global temperatures were around 3 degrees warmer than pre-industrial levels, and sea levels were dozens of feet higher than today. There is one more greenhouse gas worth understanding here, because it is in many ways more dangerous in the short run than CO2. Methane is 30 times more powerful than CO2 as an absorber of infrared radiation. The reason it doesn't dominate the conversation is that it breaks down faster. Methane reacts with oxygen in the atmosphere and is removed within around 12 years. CO2, by contrast, can persist for centuries. But right now, as Arctic permafrost thaws and wetlands warm, methane is being released in quantities that weren't part of any of our original projections. We'll come back to that. First, let's look at Venus. Venus is similar to Earth in terms of size and mass, but its surface temperature is around 460 degrees Celsius, hot enough to melt lead. Its atmosphere is mainly made up of carbon dioxide. On Venus, CO2 is no trace gas. It makes up 96.5% of the atmosphere by volume. Compare that to just over 0.04% on Earth today. Venus is what happens when the dosage spirals beyond recovery. The heat is trapped so completely that the planet reached a point where no natural feedback could reverse it. Oceans, if Venus ever had them, evaporated. The vapor added more greenhouse warming. The surface baked. The process fed itself until the planet arrived at conditions where nothing we know as life could survive. That is the textbook case of a runaway greenhouse effect. Earth is not Venus, but the direction matters. Without any greenhouse effect at all, Earth's average temperature would be about 30 degrees lower than it is today. With too much, even a relatively small addition of CO2 compared to what Venus has, the consequences compound rapidly. This is why the physics was never in serious scientific dispute. The absorption properties of CO2 were demonstrated in laboratory experiments in the 1850s by a physicist named John Tyndall. The basic mechanism has been understood and reproduced for 170 years. What was disputed, sometimes fiercely, sometimes with enormous financial motivation behind the disputing, was the attribution. Yes, CO2 traps heat, but was the extra CO2 in our atmosphere actually coming from us? That question took decades to answer definitively, and answering it required one of the most elegant forensic techniques in the history of science. For most of the 20th century, the most common objection to the idea of human-caused warming wasn't a denial that CO2 matters. It was a different argument. Maybe the warming is natural. The climate has always changed, the argument went. Temperature swings, CO2 levels fluctuate. It's all cycles, solar variation, volcanoes. How do you know it's us? For a surprisingly long time, that was not an easy question to answer. The temperature data showed warming, the CO2 curve was rising, but correlation isn't causation. The scientific community needed something more specific. They needed a fingerprint. The confirmation that rising CO2 levels come from human activity came from analyzing the types of carbon found in the air. Carbon comes in 3 isotopes. Carbon-12, making up nearly 99% of all carbon on Earth, has 6 neutrons. Carbon-13 has 7. Carbon-14 has 8. They are chemically almost identical, but they weigh slightly different amounts, and that difference in weight creates a signature. Here's the key detail. Plant matter is enriched in the lighter carbon-12 because its lower weight makes it more readily absorbed during photosynthesis. Volcanic emissions, by contrast, are enriched in carbon-13. The ratio of carbon-13 to carbon-12 in the atmosphere and ocean are roughly the same. And fossil fuels, coal, oil, natural gas, are made from ancient plant matter that has been buried for hundreds of millions of years. Carbon-14 is radioactive and decays over time. Young organic matter has plenty of it. Fossil fuels have none. 0. No measurable carbon-14 whatsoever. So if the extra CO2 entering the atmosphere were coming from volcanoes, we'd expect to see more carbon-13. If it were coming from fresh biological sources, we'd see elevated carbon-14. But what we actually see is the opposite. As CO2 concentrations have risen over the past century, the ratio of carbon-13 to carbon-12 has fallen, meaning the source of the extra carbon is enriched in the lighter isotope. CO2 from fossil fuels has lower concentrations of both carbon-13 and carbon-14 than CO2 from natural sources. Burning fossil fuels is therefore directly linked to the observed decreases in both isotopes in atmospheric CO2. This is the chemical equivalent of a serial number. Together, the ratio of the 3 carbon isotopes makes up a sample's unique isotopic fingerprint, and the carbon entering the atmosphere today bears the unmistakable print of fossil fuels. That evidence was powerful, but it still wasn't the whole picture. Knowing where the CO2 came from was one thing. Proving that this specific change in atmospheric composition was actually driving the observed warming, and not just correlating with it, required another layer of evidence entirely. That is where Ben Santer enters the story. Santer holds a doctorate in climatology from the University of East Anglia. After completing his PhD in 1987, he spent 5 years at the Max Planck Institute for Meteorology in Germany, developing and applying climate fingerprint methods. He joined Lawrence Livermore National Laboratory in 1992. In 1994, he was asked to be the convening lead author of a chapter on climate change detection and attribution for the IPCC's Second Assessment Report, the world's most authoritative review of climate science. The chapter turned out to be a critical one. The specific tool Santer's team was using came from a prediction made decades earlier. In 1967, climate modelers Suki Manabe and Richard Weatherald used a simple climate model to predict that human-caused increases in CO2 should warm Earth's lower atmosphere, the troposphere, while simultaneously cooling the upper atmosphere, the stratosphere. This is the opposite of what you'd expect if warming were driven by the sun. Solar variation would warm both layers. But greenhouse warming would trap more heat below, leaving less to reach above. The two signatures are physically distinct. Their modeling found a very distinctive feature. An increase in CO2 led to more trapping of heat in the troposphere and less heat escaping into the stratosphere, warming below, cooling above. For decades, this prediction sat waiting for data precise enough to verify it. By the early 1990s, Santer and his colleagues had that data. Weather balloons, satellite measurements, and the pattern they found matched the greenhouse fingerprint precisely. The troposphere was warming. The stratosphere was cooling, in exactly the spatial pattern that a CO2-driven signal would produce. Not the pattern of a solar cycle, not the pattern of a volcanic eruption, the pattern of greenhouse gases. The conclusion Santer and his co-authors wrote was careful, measured, and specific. The balance of evidence suggests a discernible human influence on global climate. 12 words. It was the first time the international scientific community had spoken with one voice and said, "We can formally identify a human-caused global warming signal." The response was not celebration. It was war. Many powerful interests did not like this finding, so they went after Santer. Shortly after the IPCC report was published in 1995, an industry lobbying group accused him of tampering with the report for political purposes. They engaged in a scorched earth strategy. Santer was investigated by Congress. There were calls for his dismissal from Lawrence Livermore. He was falsely accused of scientific cleansing of the report's chapter and of political tampering. He spent years setting the record straight. They argued that all sense of uncertainty had been purged from the chapter, and that the findings were based solely on two of Santer's own papers, not on the broader scientific community. Both claims were incorrect. I find this episode genuinely disturbing. Not because a scientist was attacked, that happens, but because the attack injected confusion where there was clarity, deliberately, by targeting not the science itself, but the person who communicated it. It delayed public acceptance of a conclusion that the data already supported. And it did so at a cost measured not in careers, but in years. Years when the curve kept climbing and the window for action kept narrowing. The IPCC's sixth assessment report, published decades later, made the final judgment plain. Human influence on climate is now described as unequivocal, not discernible, not probable, unequivocal. The strongest language the body uses. The most recent fingerprinting work by Santer's group confirmed that temperature changes in the stratosphere were 12 to 15 times greater than what could have been caused by natural variation. This is the clearest evidence of a human fingerprint on the climate system I've seen in 30 years of atmospheric research, Santer said. The carbon isotopes said the warming was ours. The tropospheric warming and stratospheric cooling said the warming was ours. The Keeling curve, climbing relentlessly for 65 years, said the warming was ours. Every independent line of evidence pointed in the same direction. The atmosphere doesn't lie. It doesn't have a political agenda. The CO2 in it carries the literal chemical signature of ancient plant matter burned in furnaces and engines. The heat pattern in it matches precisely what greenhouse physics predicts, and nothing else does. The warming itself is accelerating, not leveling off, not pausing. So when did the line between warming is happening and what is warming changing right now, on the ground, in the ocean, in the ice, become impossible to ignore? The answer is, it already crossed that threshold. The changes aren't coming. They're already here. In the glaciers, in the permafrost, in the chemistry of the sea. And the further you look into each of those places, the harder it becomes to look away. There is a valley in the Swiss Alps called the Rhone Valley, and at its head, where the mountains close in and the air turns sharp even in July, there is a glacier called the Aletsch. It is, or was, the largest glacier in the Alps. At its peak extent, it stretched 23 kilometers from end to end, a river of ice deep enough to bury a 12-story building under its surface. A farmer who has worked the lower pastures of that valley his whole life can walk you to a specific rock, a boulder the size of a small house, left behind by the glacier centuries ago, and point uphill. When he was a child in the 1970s, the ice came down to a certain line on the slope. You can still see where it was. The rock face above that line is polished smooth, scoured clean by the glacier's weight. Below the line, it's rough and gray, newly exposed, still learning how to weather. That line is now more than 2 kilometers behind where the ice sits today. The Aletsch has lost more than 3 kilometers of length since 1900. It has retreated more in the last 30 years than in the previous 100. A study measuring ice volume across all alpine glaciers found that they lost more than a third of their total volume between 1970 and 2023. Not a third of their length, a third of their total mass, the actual water stored in them. And the rate of loss is not slowing down. It is speeding up year after year, like a body losing weight faster the thinner it gets. Standing at a glacial moraine, the ridge of rock and debris that marks where the ice used to be, no graph can replicate what you feel. You are standing in a graveyard of frozen water that took thousands of years to accumulate. And the question hanging in the valley air isn't whether the glacier is retreating, it's how long before there's nothing left to retreat. Scientists at the Swiss Federal Institute for Forest, Snow, and Landscape Research project that more than 90% of alpine glacier volume will be gone by 2100 under current emissions trajectories. 90%. The valleys will be there. The polished rock faces will be there. The boulders will be there. The ice will not. But glaciers are only the most visible symptom. The changes happening underground in Siberia are in some ways more consequential and far less photographable. The Siberian permafrost is one of the least visited landscapes on Earth. It covers nearly half of Russia's total land area, millions of square kilometers of frozen soil, in some places frozen down to a depth of several hundred meters. It has been frozen, in places, since the last ice age. And buried inside it, preserved by the cold the way a deep freezer preserves food, is an enormous quantity of organic matter. Dead plants, animals, microbes, everything that ever lived on those landscapes over tens of thousands of years and never fully decomposed, because the cold kept stopping the process. When that ground thaws, the decomposition resumes, and as the organic matter breaks down, It releases CO2 and methane. A climate researcher working in the Yakutia region of Siberia, one of the coldest inhabited places on Earth, described driving across the tundra in early autumn and watching the ground move. Not an earthquake. The permafrost itself, thawing unevenly from below, creates massive bubbles beneath the surface layer. These structures, called pingos and thermokarst mounds, can swell to several meters high and then collapse, leaving behind craters that fill with water. When the trapped methane releases, it comes out of cracks in the mud and pools of standing water in pulses. Hold a lighter to the surface of one of those pools, and it ignites. The ground itself burns. Locals in the Yamal Peninsula in western Siberia started finding craters in the landscape in 2014. Enormous holes, tens of meters wide and deep, that appeared without warning in otherwise flat tundra. Scientists who investigated them found evidence of explosive methane release from below the permafrost. These were not small events. Some craters were large enough to swallow several houses. Katie Walter Anthony is a biogeochemist at the University of Alaska Fairbanks who has spent more than 2 decades studying methane emissions from Arctic lakes. What she found, consistently, is that the emission rates from thawing permafrost lakes far exceeded what the climate models were assuming. In one study published in 2021, her team found that permafrost carbon feedback could be twice as strong as previously estimated, meaning that for every degree of warming we cause, the permafrost releases more carbon than we expected, which causes more warming, which thaws more permafrost. The numbers embedded in this feedback are staggering. The Arctic permafrost contains an estimated 1.6 trillion tons of carbon, roughly twice the amount currently in the atmosphere. It is a carbon reservoir built over thousands of years, and it is now opening at its edges, slowly at the margins and rapidly where the thaw is deepest, releasing gases that have been locked away since before the first human beings walked across the Bering Land Bridge. It doesn't roar when it releases. It seeps, it bubbles, it exhales, quietly, from cracks in the frozen earth, in lakes lit orange under the midnight sun, in riverbeds that never used to flow in winter. The permafrost is the largest slow-motion geological event happening right now on the surface of this planet, and it is almost entirely invisible from the outside world. Beneath the surface of the water around Lizard Island on the northern Great Barrier Reef, the change has a different character. It has color. Or rather, it has the absence of color. A healthy reef is a cacophony of sensation. It sounds like a constant crackling static, the sound of thousands of snapping shrimp and grazing fish, which scientists have learned to use as a marker of reef health. It looks like architecture built from light, branching staghorns in electric blue, massive brain corals in burnt orange, table corals in luminescent green, all of it dense with movement. When a reef bleaches, the color drains out. Not metaphorically, literally. The coral's skeleton is white. Its color comes from symbiotic algae called zooxanthellae that live in the coral's tissue and produce food through photosynthesis. When water temperatures rise even slightly, by as little as 1 degree Celsius above the summer maximum, for a period of weeks, the coral expels those algae. The skeleton shows through. The coral turns white. A bleached reef is not a dead reef. Not yet. A bleached coral is an animal under extreme physiological stress, starving because it has lost its food source. If temperatures return to normal quickly enough, the algae can return and the coral recovers. If temperatures remain elevated too long, even if they eventually drop, the coral dies. The Great Barrier Reef has now experienced 6 mass bleaching events since 1998. 6. The first 4, in 1998, 2002, 2016, and 2017, were considered catastrophic by the standards of the time. Then came 2020, 2022, and 2024. 3 bleaching events in 5 years. Terry Hughes at James Cook University has been studying bleaching on the Great Barrier Reef since before the first mass event. He was the scientist who flew aerial surveys of the reef after the 2016 bleaching, one of the most severe ever recorded, and documented the damage corridor by corridor, reef by reef. Afterward, he tweeted that he cried on the plane. He is not a man prone to public displays of emotion. The data he had just flown over represented the loss of more than half the corals in the northern reef in a single summer. What was once described as a 100-year event, a bleaching so severe it kills large fractions of a reef, now arrives every few years. The reef needs at least a decade to begin recovering between events. It is not getting that time. In a warmer ocean, this mathematics is brutally simple. The gap between bleaching events is shrinking. The recovery window is longer than the gap. Reefs that cannot recover between events do not survive. The structural framework of the reef, the calcium carbonate architecture built over thousands of years, begins to dissolve in acidifying seawater. Fish leave. The cascading effect on fisheries, on coastal protection from storm waves, on the communities of people who depend on them for food and income, radiates outward across the entire Western Pacific. What the reef looks like now, patchwork, fragmented, with entire northern stretches reduced to white rubble, is, under current trajectories, the best it will ever look again for the rest of this century. Glaciers, permafrost, coral, these are the most visible faces of a warming planet. But the processes that will shape the next century are not happening on the surface. They are happening in the ocean itself. And the ocean story is one that almost no climate communication actually explains properly. The ocean has absorbed approximately 90% of the excess heat that human greenhouse gas emissions have added to the climate system since the Industrial Revolution. 90%. The air we breathe, the land we walk on, the ice we can photograph, all of that warming combined accounts for roughly 10% of the total heat entering the Earth system. The ocean absorbed the rest. Think about what that means. The temperature increases we measure in the atmosphere, the ones that have already caused droughts, broken heat records, destabilized glaciers, represent a small fraction of the total energy we have added to the planet. The ocean has been absorbing the vast majority of it. And unlike the atmosphere, the ocean holds heat for a very long time. This has implications that go in 2 directions at once. First, it means that if we stopped emitting greenhouse gases tomorrow, completely, overnight, the atmosphere would continue warming for decades, because the ocean has been taking in heat that it will slowly release back upward. The warming we have already committed to is greater than what we have observed so far. We are already locked into further change, regardless of what happens next. This is what climate scientists call committed warming. It is heat that has already been absorbed and will eventually be released. Second, it means that ocean heat content is the most honest measure of what is actually happening to the Earth's energy balance. And ocean heat content has been rising faster in the last decade than at any point in the instrumental record. The ocean is not just absorbing heat, it is saturating with it. In 2023 and 2024, ocean surface temperatures reached values that broke previous records by margins that stunned researchers. Sea surface temperatures in the North Atlantic in the summer of 2023 were so far above any previous observation that climate scientists described the anomaly in terms that suggested something qualitatively new was occurring. Not just an incremental record, but a structural departure from the range the ocean had occupied for decades. A second consequence of the ocean's role receives even less attention than heat absorption. As the ocean absorbs CO2 from the atmosphere, about a quarter of all the CO2 we emit is dissolved into seawater. A chemical reaction occurs. CO2 reacts with water molecules to form carbonic acid. The ocean becomes more acidic. Since the beginning of the Industrial Revolution, average ocean pH has dropped by about 0.1 units. That sounds tiny. pH is a logarithmic scale. A drop of 0.1 units represents a roughly 26% increase in the concentration of hydrogen ions in seawater, meaning the water is 26% more acidic than it was before industrial carbon emissions began. The ocean is acidifying 10 times faster than at any point in the last 55 million years. The organisms most directly threatened are those that build shells and skeletons from calcium carbonate: oysters, clams, sea urchins, pteropods, coral. In more acidic water, calcium carbonate dissolves more readily. It becomes harder for these animals to build and maintain their structures. Some species of pteropod, tiny snails that form a critical link in the ocean food chain, feeding everything from salmon to blue whales, already show dissolving shells in regions of the Pacific, where ocean acidification is most advanced. When a warmer ocean also becomes more energetic, when heat added to the surface layer creates stronger temperature gradients, it changes the behavior of the atmosphere above it. The atmosphere and ocean are coupled systems. What changes in one changes the other. A warmer atmosphere holds more water vapor. This is not a hypothesis or a model prediction. It's basic thermodynamics. Warmer air can hold more moisture before it saturates and precipitates. For every 1 degree Celsius of warming, the atmosphere's moisture-holding capacity increases by roughly 7%. This has no single outcome. It does not simply mean more rain everywhere. What it means is that the atmosphere is running with more fuel. Think of the atmosphere as an engine. More moisture means more latent heat available for storm systems to extract and convert to wind. When a hurricane forms over water that is 2 degrees warmer than it was 30 years ago, it has more energy to work with. It intensifies faster. Its peak wind speeds can be higher. The rainfall it dumps when it makes landfall reflects that extra atmospheric moisture loading. What is actually happening to Atlantic hurricane intensity has become one of the most intensively studied questions in climate science. What researchers have found is that the proportion of Atlantic storms reaching the highest categories, Category 4 and 5, has increased significantly since the 1980s. Individual storms are not necessarily more frequent, but the ones that do form are more likely to reach extreme intensities. Rapid intensification, when a hurricane's winds increase by 35 miles per hour or more in 24 hours, has become more common. Hurricane Patricia in 2015 intensified from a tropical storm to a Category 5 hurricane in 24 hours. When it reached its peak intensity over the eastern Pacific, it became the most powerful tropical cyclone ever recorded in the Western Hemisphere, with sustained winds of 215 miles per hour. The compounding effect is this. Warmer oceans drive more intense storms, which dump more rainfall because the atmosphere above the storm is also carrying more moisture, which produces catastrophic flooding that older flood models did not anticipate, and that older infrastructure was not built to handle. In Houston, Texas, floods that were once classified as 500-year events, meaning they had a 1 in 500 chance of occurring in any given year, have happened 3 times in 3 years. The statistical category became meaningless almost overnight. The infrastructure of the city, its drainage systems, its floodplains, its zoning decisions, was built around a historical baseline that no longer exists. The flooding that hit the Ahr Valley in western Germany in July 2021 is one of the defining climate disasters of the early 21st century. The region had flood warnings going back to the previous day, but the scale of the event exceeded anything in the recorded history of the valley. In a period of hours, the Ahr River rose to heights never measured in modern records. 135 people died. Entire villages were erased. A family in the town of Schuld photographed in front of their home, a house their grandparents had built. After the flood, stood looking at foundations exposed down to bare stone. The building was gone. Not damaged. Gone. The family had lived in that valley for generations. The floods they knew from childhood were minor events. A meter of water in the basement, gone in a day. What arrived in July 2021 was something no one in that valley had a mental model for. Attribution science, the field that asks how much more likely or intense a given extreme weather event was made by climate change, found that the rainfall intensity that produced the R Valley flooding was made 40 to 60% more intense by the additional moisture content in a warmer atmosphere. 40 to 60% more intense. That gap, translated into human terms, is the gap between a flooded basement and a missing house. The drought side of this equation is just as severe, and it operates by the same mechanism in reverse. More moisture in a warmer atmosphere means it concentrates where it falls, but it also means that regions between wet zones dry out faster. Higher temperatures mean higher evaporation rates from soil and vegetation. A drought that would have lasted 2 years under pre-industrial conditions can last 5 years when background temperatures are 1.5 degrees higher, because the soil moisture deficit is continuously reinforced by the extra warmth. The western United States has been in a mega drought. That is, a drought more severe than anything in the past 1,200 years of tree ring and sediment records, for more than 2 decades. The Colorado River, which supplies water to 40 million people across 7 states, has been running at roughly 50 to 60% of its historical average flow for most of this century. Lake Mead, the largest reservoir in the United States, dropped to its lowest level ever recorded in 2022, low enough that boats that sank in the 1930s when the reservoir was first filling re-emerged from the mud. And wildfires. A wildfire in a dry, hot landscape is not a new phenomenon. But there is a measurable, quantifiable shift happening in the fire behavior of forests across the American West, the Mediterranean, Australia, and Siberia that goes beyond scale and into category. The combination of drought stress, earlier snowmelt, higher summer temperatures, and wind patterns shifted by warming has extended what used to be a fire season of 2 or 3 months into something closer to a year-round state of elevated risk. The Camp Fire in California in November 2018 killed 85 people, made it the deadliest wildfire in California history, and was driven by a set of atmospheric conditions: record low humidity, fierce Diablo winds, extreme dryness after a wet winter that had grown dense vegetation, which then dried through a brutal summer, that researchers described as the new template for extreme fire events in the western United States. Not the rare exception, the template. Each of these processes, glacier retreat, permafrost thaw, coral bleaching, ocean heat absorption, atmospheric moisture loading, drought intensification, wildfire expansion, is concerning in isolation. But the reason climate scientists use the word acceleration is not simply because each one is getting worse. It's because they interact. They feed each other. And the interactions are where the real danger lives. Start with ice. Arctic sea ice reflects somewhere between 50 and 70% of incoming solar radiation back into space. Dark ocean water, by contrast, absorbs over 90% of it. As the Arctic warms and sea ice retreats, the newly exposed ocean absorbs vastly more heat than the ice it replaced did, which warms the Arctic faster, which melts more ice, which exposes more ocean. This is the albedo feedback. It is not a future scenario. The Arctic is warming at roughly 4 times the global average rate, and a major reason is this exact mechanism running continuously. The albedo feedback has an endpoint. When the Arctic Ocean is seasonally ice-free in summer, the feedback reaches its maximum forcing. In 2023, Antarctic sea ice extent broke records by such large margins that researchers described it as statistically extraordinary, well outside the range of natural variability in the satellite record. The Southern Ocean ice area dropped to its lowest ever measured extent. Both poles are losing the reflective surface at once. Then there is the carbon feedback from warming soil. As temperatures rise, soil microbes become more active and decompose organic matter faster, releasing more CO2. This happens not just in permafrost, but in temperate soils globally. A set of studies examining soil respiration rates globally found that warming is accelerating the breakdown of carbon stores in soils far more broadly than models had assumed. The land surface, which was once a reliable carbon sink, is becoming less reliable at absorbing carbon as temperatures increase. The third feedback loop is the one that concerns researchers the most in the medium term: methane clathrates on the ocean floor. Methane clathrate is a compound of methane and water ice that forms under specific conditions of temperature and pressure, mainly on continental shelves at depths where the water is cold enough to keep the compound stable. The shallow Arctic shelf, particularly the East Siberian Arctic shelf, contains enormous quantities of this material. As Arctic Ocean temperatures rise and bottom water warms even fractionally, the clathrates destabilize and release methane directly into the water column, and eventually the atmosphere. Natalia Shakova at the International Arctic Research Center in Fairbanks has been measuring methane flux from the East Siberian Arctic shelf since the early 2000s. What her team documented was that the seafloor was releasing methane at levels far higher than expected, and that large seeps, which had previously been considered rare, were common across wide stretches of the shelf. In some locations, the methane was rising in plumes visible in sonar imaging. The question of whether this release will remain gradual, or whether warming could trigger a sudden large-scale destabilization of clathrate fields, sometimes called a methane pulse, remains one of the most actively debated open questions in Earth system science. Then there is the Amazon. The Amazon rainforest contains approximately 180 billion tons of carbon stored in its vegetation and soils. It is not just a carbon store, it is an active part of the water cycle. The forest generates its own rainfall through transpiration. Trees in the Amazon release water vapor that forms clouds, which drop rain, which waters the trees. The Amazon creates its own weather. This recycling system depends on the forest being intact. Above a threshold of deforestation, estimates put this threshold somewhere between 20 and 25% forest loss, the recycling begins to break down. Rainfall decreases. The forest dries. Dry forest burns. Burned forest releases carbon. Less forest means less moisture recycling. The system tips from being a carbon sink to being a carbon source. Current estimates put Amazon deforestation at around 17 to 20% of the original forest cover. The region is approaching the threshold. And in 2023, portions of the Amazon experienced their worst drought ever recorded. Rivers that have sustained indigenous communities for millennia dried to expose their sandy beds. Fish died by the millions. In some towns, the only access was by boat, and the boats couldn't reach them. A study published in 2023 found that the southeastern Amazon has already flipped. That specific region is now releasing more carbon than it absorbs, due to the combination of deforestation, fire, and drought stress. The whole basin hasn't flipped yet, but part of it has. None of these feedback loops are hypothetical future risks. The albedo feedback is running right now. The permafrost carbon feedback is running right now. The Amazon is under stress right now. The ocean heat content is rising right now. They are not dominoes set up in a line waiting for a push. They are dominoes already in motion, some of them already falling, knocking into each other in ways that are producing consequences faster than any single one of them would have on its own. This is why the vocabulary of climate science has shifted over the past decade. It's not just warming. It's not just change. It's destabilization. The removal of the conditions of stability that allowed agriculture to develop 10,000 years ago, that allowed cities to be built in the locations they were built, that allowed a specific set of species assemblages and weather patterns to persist long enough for human civilization to depend on them. When you add all of this up, the retreating ice, the thawing soil, the acidifying ocean, the loading atmosphere, the accelerating feedbacks, and you translate them into a single question, how much hotter and how fast, you arrive at the part of the science that is the most debated, the most politically charged, and the most consequential. The projections. The numbers that describe not what has already happened, but what is coming. And what the difference between 2 degrees and 3 degrees actually looks like when you put a specific city, a specific coastline, a specific crop system underneath those numbers. James Hansen was sitting in front of the United States Senate Committee on Energy and Natural Resources on June 23, 1988, when he said something that had never been said in that room before. It was the hottest June day in Washington, D.C. in recorded history. The air conditioning in the hearing room was reportedly broken. The senators were sweating through their suits. And Hansen, then director of NASA's Goddard Institute for Space Studies, looked at the committee and said, "The greenhouse effect has been detected, and it is changing our climate now. Not maybe changing, not could potentially affect, now." The committee heard him. The press covered it. It made the front page of the New York Times. And then, for the next 35 years, the world argued about what to do, while the curve on Keeling's wall kept climbing, the ice kept retreating, and the ocean kept warming. Hansen had run his climate models and produced temperature projections stretching to the end of the 21st century. In 1988, those projections seemed distant, abstract. They described a future far enough away that it could be treated as someone else's problem. That future is now. The projections Hansen made are not predictions anymore. They are, in many cases, the record we are living in. And the question that climate science is now wrestling with is not whether warming will happen. It is how far down 3 different roads we are actually going to travel. Because those roads lead to genuinely different worlds. Not different in degree, but different in kind. The first road is the one we keep calling the target, 1.5 degrees Celsius above the pre-industrial baseline. This is the number at the center of the Paris Agreement, the number that 200 countries signed onto in 2015, the number that has appeared in more policy documents and international communiques than any other in the history of climate diplomacy. What does 1.5 degrees actually look like on the ground? It is important to be honest about this. 1.5 degrees is not a safe world. It is a less catastrophic world. At 1.5 degrees of global average warming, which we are already very close to touching in individual years, coral reef systems globally decline by 70 to 90% compared to pre-industrial conditions. Arctic summers become ice-free at least once per decade. Approximately 700 million people face exposure to severe heat waves at least once every 5 years. Crop yields of maize, rice, wheat, and other major crops decline across subtropical regions. Sea levels continue to rise for centuries, regardless of what happens to emissions, because the heat already in the ocean will continue driving thermal expansion and ice melt. A farmer in Bangladesh growing rice on delta land that sits less than a meter above current sea level and there are millions of people in that exact position, does not hear 1.5 degrees and think, safe. She hears it and calculates, how many more years before saltwater intrusion makes this soil unfarmable? 5? 20? Does she invest in seeds for the next planting? Or does she start saving for the bus ticket to Dhaka? 1.5 degrees is described as a target because it is the threshold below which the worst feedback dynamics remain less likely to fully activate. It is the line drawn not because everything is fine below it, but because above it, the territory becomes genuinely harder to navigate. And here is the brutal truth about that target. We are almost certainly going to exceed it. Global average temperatures already touched 1.5 degrees above pre-industrial levels in 2023 and held above that threshold for the entire calendar year of 2024. The world has not formally passed the Paris threshold, which is measured as a long-term average over decades, not a single year. But every climate model, every emissions trajectory, and every measurement of current CO2 concentrations points in the same direction. To stay below 1.5 degrees on a sustained basis, global emissions would have needed to begin falling sharply around 2020 and reach net zero by roughly 2050. They have not fallen. In 2023, global CO2 emissions hit a new record high. The International Energy Agency reported that, despite record deployment of solar and wind power, total fossil fuel consumption continued to increase globally in 2023. The curve has not bent. Not yet. 2 degrees is where the scientific literature begins using language that is harder to soften. The difference between 1.5 and 2 degrees sounds small, half a degree. Translated into planetary consequences, it is not small at all. At 2 degrees, the proportion of the global population exposed to extreme heat stress at least once every 5 years rises from roughly 14% to roughly 37%. That is the difference between a regional crisis and a global one. At 2 degrees, the decline in coral reefs shifts from severe to near total. Upward of 99% of tropical reef systems are projected to experience annual bleaching conditions. At 2 degrees, the Greenland ice sheet is considered to be above its threshold for irreversible long-term destabilization, meaning that even if warming eventually reversed, the ice sheet would continue melting for centuries because the feedback mechanisms keeping it stable have broken down. A city like Miami illustrates what this means at street level. It sits on porous limestone bedrock. You cannot build a seawall around Miami that actually stops the ocean because the water rises through the ground itself. It comes up through the drains, through the parking lots, through the streets during high tides, even on clear days. This is called sunny day flooding, and it already happens dozens of times a year in parts of Miami Beach. At 2 degrees of warming, sea level rise projections for the region by 2100 range from roughly 0.5 meter to 1 meter above current levels, with the lower end of that range representing several $100 million of annual flood damage, and the upper end threatening the basic infrastructure of a metropolitan area of 6 million people. The people making decisions in Miami today, engineers, city planners, real estate developers, insurance actuaries, are not making decisions about whether climate change is real. They are making decisions about how much time they have and what to protect first. The insurance market has already begun making its own assessment. Several major insurers have withdrawn from Florida entirely in the last few years, unwilling to price the risk at any premium a homeowner could afford to pay. 2 degrees is, under current policies and pledges, roughly where the world is on track to arrive. Not if things go badly. Under current plans, accounting for the commitments nations have actually made and the degree to which they are implementing them, median projections cluster around 2.5 to 3 degrees by 2100. 3 degrees is where the language in the scientific literature shifts again, and the shift is not subtle. At 3 degrees, large parts of the subtropics and tropics become genuinely difficult to live in during summer months. The combination of heat and humidity creates conditions that exceed what the human body can tolerate in the open air. Conditions where a healthy adult cannot cool themselves through sweating, even in shade, because the air itself is too hot and humid to absorb body heat. These conditions, measured using a metric called wet bulb temperature, already occur briefly in parts of South Asia, the Persian Gulf, and sub-Saharan Africa. At 3 degrees of global warming, they become seasonal realities across large areas where hundreds of millions of people currently live and farm. The agricultural system at 3 degrees faces stresses that are qualitatively different from what we face today. Crop failure years, where yields drop by more than 25% across major production regions simultaneously, become significantly more frequent. The historical assumption embedded in global food markets is that bad harvest years in one region are offset by good years elsewhere. 3 degrees of warming, combined with the atmospheric moisture dynamics we have already discussed, increases the probability of synchronized failures, bad years everywhere at once, to levels that the current food distribution system was not designed to handle. A researcher at the Potsdam Institute for Climate Impact Research described this risk in terms that I find deeply unsettling. She was talking about what the models show in the tail of the probability distribution, the scenarios that are not the most likely outcome, but are not negligible either. At 3 degrees, she said, some of the low probability, high impact scenarios involve stress on global food supply severe enough that the political consequences become the primary driver of cascading harm. It is not just that crops fail, it is that crop failure interacts with debt, conflict, migration, and political instability in ways that amplify each other. Famine and war have always been connected. What changes at 3 degrees is the frequency and simultaneity of the triggers. I want to be precise here, because I do not want to be alarmist in a way that is dishonest. 3 degrees is not a certainty. It is where current policies lead if nothing changes. And things are changing. Slowly, inconsistently, inadequately, but genuinely. The tipping points are the part of the story where the science moves fastest and where the uncertainty is widest. And they're the part where, if you spend enough time with the data, the feeling of urgency becomes hardest to set aside. A tipping point in climate science is a threshold in a physical system beyond which change becomes self-sustaining, no longer driven by external forcing, but by the system's own dynamics. The classic example is an ice sheet. Below a certain size, an ice sheet is stable because its high altitude keeps it cold. But if warming reduces the ice sheet enough that its surface drops to lower, warmer elevations, the melt accelerates under its own logic. Lower elevation means more warmth, more melt, lower elevation still. The system tips. The West Antarctic ice sheet is the one that keeps polar oceanographers awake at night. It is a marine ice sheet, meaning it is grounded on bedrock that sits below sea level. Its base is in contact with ocean water. As ocean temperatures rise, that ocean water is melting the ice from below, at the grounding line where ice meets rock meets sea. Researchers working in the Amundsen Sea embayment, the most vulnerable sector, have documented that warm circumpolar deep water is now regularly reaching the base of key glaciers, including Thwaites and Pine Island, causing melting rates that have no precedent in the observational record. Thwaites Glacier is sometimes called the Doomsday Glacier by science journalists, which is a term that annoys scientists, but the underlying concern is real. Thwaites alone contains enough ice to raise global sea levels by roughly 65 centimeters, about 2 feet if it fully destabilized over centuries. But Thwaites also acts as a buttress for the broader West Antarctic ice sheet. Its collapse over a long time frame could unlock additional ice equivalent to several more feet of sea level rise. A study published in 2021 found evidence of a warm water cavity beneath Thwaites' main glacier that hadn't been observed before. Direct ocean access to the base of the ice. The complete destabilization of the West Antarctic ice sheet would not happen in a decade or a generation. But the tipping, the point at which the process becomes irreversible regardless of what happens to emissions, may be much closer. Current research suggests the threshold for irreversible WAIS destabilization sits somewhere in the range of 1.5 to 2 degrees of global warming, with significant uncertainty in both directions. We are already at that temperature in peak years. The science does not say the system has tipped. It says the margin between where we are and where it tips is narrower than almost anyone expected a decade ago. Then there is AMOC, the Atlantic Meridional Overturning Circulation. This is the system of ocean currents that moves warm surface water from the tropics northward through the Atlantic, releases heat into the atmosphere over Europe and the North Atlantic, and returns as cold, deep water flowing south. It is the engine that keeps northern Europe habitable at its latitude. Without it, winter temperatures in the United Kingdom and Scandinavia would be considerably colder than they are today. It is also one of the drivers of the monsoon patterns that deliver rainfall to the Sahel and to South America. AMOC is slowing. Measurements of the current using ocean sensors, satellite data, and proxy records going back centuries indicate that AMOC has weakened significantly since the mid-20th century and is now at its weakest point in at least 1,000 years. The mechanism driving the slowdown is precisely what the climate models predicted. Fresh water from melting Greenland ice is flooding into the North Atlantic, disrupting the density difference between warm and cold water that drives the circulation. Fresher water is less dense, sinks less readily, and slows the conveyor. A study published in 2023 used statistical analysis of sea surface temperature patterns to estimate when AMOC might collapse entirely if the current trend continues. The result, which the authors described as uncertain but in a direction that demanded attention, put a possible tipping somewhere between 2050 and 2100, with the earlier end of that range representing a meaningful probability under high emissions scenarios. What does an AMOC collapse look like? It is not a single dramatic moment. It is a slow unraveling over years, followed by a rapid reorganization of ocean circulation. For Europe, the short-term cooling effect would partly offset greenhouse warming in some regions, but the disruption to monsoon systems globally, to fisheries in the North Atlantic, and to rainfall patterns across West Africa and South America would represent consequences felt on every inhabited continent. An oceanographer who has spent 2 decades tracking the deep water formation sites in the Labrador Sea, where cold, dense water sinks and feeds the overturning circulation, described watching the deep convection events become shallower and less frequent. Less water sinking, less circulation. Each year, the pattern looks a little more like what the models predicted for a weakening system. She told a colleague that the data now keeps her up at night in a way it didn't a decade ago. Not because of a sudden change, because of the absence of a recovery she had expected to see. The Paris Agreement was signed in 2015. 196 parties. The stated goal? Limit global average temperature increase to well below 2 degrees above pre-industrial levels, and pursue efforts to limit the increase to 1.5 degrees. The agreement was voluntary, with each country setting its own emissions reduction targets, nationally determined contributions, and being held accountable through transparency mechanisms rather than enforcement. The climate diplomats who negotiated the agreement knew it was insufficient at signing. The pledges made in Paris in 2015, if fully implemented, were estimated to put the world on track for approximately 3 degrees of warming. Not 1.5, 3. The logic behind signing a legally inadequate agreement was that it established a framework, that the commitments would ratchet upward over time, that countries would return every 5 years with stronger pledges, and that the agreement would set in motion technology shifts and political dynamics that would drive faster action. The person I think of when I consider this bargain is Christiana Figueres, the Costa Rican diplomat who served as executive secretary of the UN Framework Convention on Climate Change from 2010 to 2016, and who was the primary architect of the Paris Agreement. She took over the role 18 months after the catastrophic failure of the Copenhagen Climate Summit in 2009, a summit that was widely seen as the moment international climate diplomacy had collapsed. She described the state of the process when she took over as somewhere between dysfunctional and dead. What she did over the next 5 years is one of the most consequential acts of sustained political will in the history of international diplomacy. She shifted the negotiating framework from one built on the idea of a legally binding top-down treaty, which had failed repeatedly, to one built on voluntary pledges and peer accountability. She pushed for major emitters to announce pledges before Paris rather than at it, so that no country could arrive as a free rider. She personally lobbied heads of state, finance ministers, and business leaders. She kept the process moving when it seemed on the verge of collapse at least 3 separate times. The agreement that emerged was imperfect. She said so herself, publicly, immediately after it was signed. But it was real. It was universal. And it set a baseline from which harder commitments could eventually be demanded. Since Paris, the trajectory of renewable energy has moved faster than almost any pre-agreement model projected. Solar power costs have fallen more than 90% since 2010, faster than any technology in history. Wind power costs have fallen similarly. In 2023, global clean energy investment exceeded $1.7 trillion, more than was invested in fossil fuels for the first time ever. Electric vehicle sales are growing at a rate that no major automaker's internal projections from 10 years ago anticipated. This is real. It is not sufficient, but it is real, and it matters. The problem is physics. Physics does not care about investment rates. Physics cares about cumulative concentrations of CO2 in the atmosphere. And the carbon budget, the total amount of CO2 we can emit before the 1.5-degree threshold is statistically locked in, has been shrinking every year, including the years in which renewable energy deployment has accelerated. We are building solar panels and natural gas pipelines simultaneously. We are deploying wind turbines and approving new oil fields simultaneously. The energy transition is real. It is not yet happening fast enough to change the direction of the curve that Keeling started measuring in 1958. There is a conversation that happens inside climate science, usually not in papers, but in corridors, in late conference evenings, in the kind of talk between researchers that doesn't end up in the abstract of a journal article. It is the conversation between adaptation and mitigation. And it is, in some ways, the most honest and the most difficult conversation in all of this. Mitigation means reducing emissions, preventing future warming from occurring. Adaptation means adjusting to warming that is already happening or locked in, building seawalls, shifting crop varieties, relocating populations, redesigning cities. The tension is this: every dollar spent on adaptation today is a dollar not spent on mitigation. But every degree of warming that mitigation prevents is also a degree that does not require adaptation. They are not in pure opposition, but they pull in different directions when resources are limited. A coastal engineer working on flood barrier design for a major delta city in Southeast Asia, somewhere like Ho Chi Minh City or Dhaka, faces a version of this choice that is not abstract. She is designing infrastructure to protect 10 million people from sea level rise that is already occurring. The barriers will cost billions of dollars and take decades to build. To design them, she has to commit to a sea level scenario. How much rise? By when? If she designs for 0.5 meter and the real rise turns out to be 1.5 meters, the barriers will be inadequate before they reach the end of their design life. If she designs for 2 meters and the real rise turns out to be less, billions were spent on overbuilt infrastructure. The uncertainty in the projections is not a failure of climate science. It is an honest reflection of the fact that what happens to sea levels depends partly on decisions being made right now about emissions, about tipping points, about policies that haven't been written yet. She is designing for a future that depends on choices other people will make. She does not know what those choices will be. She builds the best barrier she can for the most likely range of scenarios, and she knows, professionally, technically, clearly, that it may not be enough. That position, clear-eyed, working on the best available information, building toward a future that remains genuinely uncertain, is not unique to coastal engineers. It describes the condition of almost everyone doing serious work in this space. Not paralysis, not false confidence, a very specific kind of calculated urgency. Moving as fast as the knowledge allows, knowing the knowledge is incomplete. The people who work in carbon dioxide removal, direct air capture, enhanced weathering, ocean-based carbon sequestration occupy a similar space. The technologies exist. They are expensive. The leading direct air capture facilities currently operating can remove tens of thousands of tons of CO2 per year. Global emissions are currently around 40 billion tons per year. The gap between current capability and required scale is not a gap in principle. It is a gap in deployment speed, in investment, in political will, in time. A researcher at a leading carbon removal startup described the feeling of running models that show a path to limiting warming to 1.5 degrees that includes significant carbon removal, and then running the deployment math on how fast those facilities would need to be built. The conclusion is not that it's impossible. The conclusion is that the window in which it remains technically possible is extremely narrow, and narrowing further every year we delay. The window doesn't close like a door. It narrows like a corridor that is slowly filling with water. You can still move forward. You just have less room to do it. Let me tell you what the models show at the current trajectory. Not the worst case, not the best case. The central estimate, given current policies and the realistic expectation that clean energy deployment continues at roughly its current pace. We are likely to reach 2 degrees of global average warming somewhere between 2040 and 2060. That range reflects genuine uncertainty in the climate system, how fast feedbacks accelerate, how quickly clean energy deployment cuts into emissions curves, whether there are surprises in either direction. At 2 degrees, the things we discussed, mass coral bleaching as a permanent condition, increased frequency of extreme weather events, accelerating sea level rise, heat stress across the subtropics, become baseline reality rather than exceptional events. The countries that will experience the consequences most severely are not, in general, the countries that produced the most emissions. Sub-Saharan Africa, South and Southeast Asia, small island states in the Pacific and Indian Ocean. These regions produced a fraction of historical cumulative emissions and face some of the most acute consequences. A citizen of Bangladesh has contributed roughly 1/30th the cumulative emissions of a citizen of the United States over the past century. The 2-degree world will not be 2 degrees for everyone equally. For Bangladesh's coastal regions, the combination of sea level rise, cyclone intensification, and monsoon disruption represents an existential threat to the way of life that has existed there for generations. This is perhaps the most morally complicated part of the entire story, and I find that no amount of data makes it easier to sit with. The people who caused the least harm are positioned to experience the most harm. And they are asking, in international negotiations, in UN speeches, in climate finance discussions for the countries that industrialized first to help fund adaptation in regions that cannot afford it alone. The responses have been inadequate. Loss and damage funding, agreed at COP in 2022 after 30 years of negotiation, represents a fraction of what would be needed. I am not going to soften that. And yet, the cost of solar power has fallen by 90% in 14 years. 14 years. That is faster than any energy technology in human history. The projections that informed policy in 2010 did not anticipate this. The models are updated. The trajectory has genuinely shifted. In 2022, the United States passed the Inflation Reduction Act, allocating roughly $370 billion toward clean energy over 10 years, the largest climate investment in American history. The European Union has committed to cutting emissions by 55% by 2030, compared to 1990 levels. China, which now produces more solar panels than the rest of the world combined, has pledged to peak its emissions before 2030 and reach carbon neutrality by 2060. None of these commitments are sufficient on their own. All of them together represent a world that is genuinely changing direction, even if the change is not yet fast enough to match the scale of the problem. The one thing that climate scientists consistently say when asked about hope, in interviews, in recorded panel discussions, in the places where careful, measured researchers allow themselves to speak honestly, is that the difference between 2 degrees and 3 degrees represents hundreds of millions of people whose lives, livelihoods, and homes are preserved or destroyed. The difference between 2.5 and 2 degrees is hundreds of millions of people. Every fraction of a degree matters. Every year the curve bends earlier matters. The worst outcome is not inevitable. It must be chosen or avoided, one decision at a time. If you want to stay close to this conversation, as the science moves forward, as the politics shift, as the technology deploys and the feedbacks unfold, subscribe. Every video on this channel takes a subject that matters and tries to explain it the way it actually is, not the way it's easiest to say. This one was hard to write. It should be. I want to end not with a number or a policy recommendation or a call to action. I want to end with an image. There is a photograph taken above the Aletsch Glacier in the Swiss Alps. It was taken from the same position, from a peak above the ice, in 2 different years, once in 1930 and once in 2020. The earlier photograph shows ice filling the entire valley from wall to wall, a white highway of compressed centuries. The later photograph shows the same valley, the same rock walls, the same sky. And in the center, diminished, narrowed, retreated up into the higher reaches of the mountain, the remnant of the ice. The rock in between is not empty. It is covered in vegetation now, colonizing the newly exposed ground. Mosses, then grasses, then shrubs, then, eventually, the first stunted trees. Life moving into spaces that were ice within living memory. Both things are true at once. The loss is real, measurable, and accelerating. And the ground the loss exposes is being claimed by something else. Not as consolation, not as replacement, but as evidence of what happens when conditions change, that life, in its relentless and indifferent way, finds the new edges and begins again. We are living in one of those edges right now. The question that remains, and that will not be answered in this video, or the next, or the decade after, is whether we have the capacity to choose the shape of what comes next. Not to stop change entirely, that window has narrowed too far, but to choose the magnitude, to choose how much of the old world we preserve inside the new one. The curve on Keeling's wall has not stopped climbing, but the rate at which we are adding to it is beginning, slowly, insufficiently, genuinely, to slow. That is not victory, but it is not nothing either.